This video introduces the PICL, the Portable In-Circuit Learner. The PICL is an electronic component that supports basic machine learning. Users wire it into a circuit, then train it by demonstrating example input and desired output. As an example, we attach a light-sensing cell to the PICL. In this example, we'd like the light to turn on when our shadow covers the sensor. We cover the sensor, capture the input, then indicate that we'd like 5 volts as output when the input is seen. Finally, we save the example. Next, we capture the ambient light level and indicate that we wish the output to go to 0 volts when seeing this input. Internally, the PICL uses a support vector machine to create a linear classifier using these two examples. Next, we'll attach the output of this circuit to a transistor that acts as a switch. Here we've wired leads onto a button on this toy keyboard. When we cast a shadow, we trigger the playback of this keyboard. We could also swap out this light sensor for a proximity sensor. The proximity sensor is an active sensor, which means it requires power, but it outputs out voltage directly. As before, we train the system and are now able to trigger the keyboard using proximity. The PICL provides a number of features for streamlining training. If the user is able to demonstrate example input while at the same time accessing PICL's interface, they can simply press the desired output value while demonstrating the input. The PICL also automatically infers a baseline. When it first starts up after being reset, the PICL samples the input and records it as a baseline signal. Then, after receiving the first training example, it assumes the earlier baseline reading is the opposite example. Some input signals are transient and are difficult to mark by the user. For example, the sound produced by knocking on the table. To assist in training on such transient input, the PICL tracks the minimum and maximum values attained by the input signal. It then determines which of these values provides the best separation of the data. The PICL is fast enough to detect other camera flashes. By attaching an external flash unit, we can recreate drawings privacy-preserving spaces. Here, a defensive flash is triggered by the photographer's camera and the picture is washed out. The other training mode supported by the PICL is linear regression. In this example, we create a fan whose speed is varied depending on the temperature read by a thermistor. We train the fan to turn on when the thermistor reads a high temperature and to turn off when the temperature is reading low. As the thermistor cools to room temperature, the fan slows down gradually. PICL continually maps its input to output with no further processing. In many cases, this mapping is sufficient. However, there are a number of times when it is desirable to process the output in some way. For that reason, we developed a number of output adapters. As an example, if we wish to create a basic alarm system built off a laser trip line, we would like the alarm to continue to sound after the laser has been tripped. For this circumstance, we can use a latched output adapter. When the latched output adapter is triggered, it remains in a high state until it is manually reset. Many buttons on devices require the user to depress them for a minimum amount of time before they respond. This is called debouncing. For these circumstances, we can use a pulsed output adapter which outputs a pulse for a period of time after receiving a high input. If you would like to turn on a light or appliance with a clap, we can interface the pulsed adapter with a remote-controlled power outlet. We can also replace the pulsed output adapter with a toggle adapter and directly control various small devices such as this fan. Our final output adapter outputs an oscillating signal as a function of the input voltage. In this example, we attach a light sensor to the PICL and use it to vary the speed with which the drum is struck on the keyboard. In addition to the output adapters, the PICL can interface directly with a number of electronic toolkits. As an example, we added the littleBits magnetic interface to PICL. littleBits are a recent hardware prototyping platform for those with no experience in electronics. littleBits includes numerous sensors and actuators, but provides no logic or computational unit. The PICL with the littleBits interface provides a low-barrier way to add computation to the littleBits platform. In this example, we train the PICL to invert the analog output provided by the littleBits pressure sensor.